All right. Good morning, everybody, and thanks for the invitation. And thanks, Benjamin, for switching on short notice in the talk. I have to give a lecture, my teacher in basically an hour time, which would have been a bit tight. So that helps me a bit. Okay, so I would like to tell in the next half hour about our experiments on KPZ universality and introduce you first a little bit to our tools of the trade, our quantum gas microscopes, the control we have in these systems, and the potential engineering that we use, and then apply this to this KPZ phenomena that we have been studying based on recent numerical work, mainly from Tomasz Prosen's group in Ljubljana, and then many others following this track. Okay, so let me start with quantum gas microscopy, tell you a little bit about that. It basically allows us to get high resolution images of many body wave functions or density matrices in the system, allowing us to detect occupations on individual lattice site in an optical lattice, and do that, as we'll see, actually with full spin and density resolution. So here's a picture of how this typically works. We have a high resolution microscope objective. We prepare our atoms in these optical lattices, mostly in a single plane, to have them within a depth of focus of the objective. And then we just, when we want to detect them, we scatter resonant light off them so they fluoresce, simultaneously are cooled via an optical molasses or Raman cooling. And then we can capture the fluorescent and see the atoms in these optical lattices. So I should say this works with close distances to the atoms down to 700 nanometers or 500 nanometers, where you can see the individual atoms. This makes it much harder than, for example, in tweezer experiments, where you have much larger separations between the atoms, where you can basically scatter only a few photons to reliably detect an atom. So when the atoms come very close together and you still want to resolve them, you actually have to do a little bit more on the resolution side to see them with good signal to noise in the system. Now, if you can see them, you can also manipulate them. And this is kind of the reverse thing that we can do. We can focus laser beams onto the atoms and manipulate them. And we'll talk about that in a second. And we can basically project arbitrary potentials onto the atoms. So this is interesting now for the dynamics aspect or disorder aspect also, because we can project, for example, controlled potentials like this lattice potential or these two boxes connected by a wire, something that Tilman Esslinger is doing very successfully in Zurich, or as what we're going to use in this talk, really confine the systems in pure box potentials. So there's no harmonic confinement anymore. There's flat potentials that we can study these systems in. Now, for a disorder perspective, I just want to mention being able to, to controllably project the disorder onto the system is, of course, nice, because you can engineer, for example, also distinct types of correlated disorder into the system if you want to study that. So here's a picture of how this works in the experiment. So we have our optical lattice, and on top of that, we superpose a shaping pattern. This is generated by turning the, for example, mirrors in this digital mirror device, this spatial light modulator, on and off. So each white pixel here would mean there's a mirror that is tilted, and black would be the mirror is not tilted. We shine a laser beam onto this DMD device. This is then the light field that we get out. We superimpose that on top of the optical lattice, and then we can take these fluorescence images I talked about, and then we see these pictures where you see each individual atom in the lattice. And then, for example, you can take thousands of these images and measure correlation functions, as we'll see, or you can just calculate the average density, like shown here, to see that the potential is really nicely homogeneous and flat. Yeah, so now we can do this with quite large system sizes. So we can do this with up to system sizes of a few thousand particles in these lattices in flat potentials. So these are circular potentials, circular confining potential on a square lattice, where the system size is 1,000 to 2,000 particles. And we can cool the system by dumping, the hot atoms, evaporating them off, or dumping them into an entropy reservoir. So the remaining atoms in the system are rather cold and allow us to study what we want to study in the experiment. So just for the detection, let me show you actually that one nice method we developed recently on our fermionic quantum gas microscope is basically the idea to fully detect spin and charge resolved images of those atoms on those lattices. So imagine you have a Fermi-Hubbard system, which looks like this in 2 dimensions, spin ups and downs, holes and doublons. And now you want to detect them. And the idea how we do this is we basically apply a Stern-Gerlach separation and split each physical layer of the system that we want to study into two detection layers, where the upper detection layer is only occupied by spin-up particles and the lower detection layer only occupied by spin-down particles. And then by taking subsequent images of those two layers, we can reconstruct the original occupation of the system. Now, I don't want to say too much how that works. There's some interesting topological pumping actually involved in this process, so it could have been interesting for this workshop as well. I just want to show you images, how this works. So here's the conceptual idea again. We have the physical system, we split it, we first focus our detector onto the lower plane, then we focus onto the upper plane, all the same snapshot of the system, and then we record the atoms in the lattice. So let me show you pictures of this. So here's this split system where we separated the layers over a large distance so we can image them separately. And then you basically see, for example, the spin-up atoms here, the red ones, the spin-down atoms in the lower layer. These are the two reconstructions of where they sit on the lattice. And when we put those two reconstructed images together, we find actually the full configuration of the system of that snapshot. So we can see fully where a spin up is, a hole is, a doublon is. So we get full spin and charge or density resolution, if you wish, in this system. Yeah? And this is nice, especially if you want to study the interplay of hole with a magnetic background, for example, because this is the information you need. You need to know, how does a hole interact with the magnetic environment surrounding it. All right, so that's all I want to say about the ideas how to detect these systems. So let me move on to the actual experiment then on this KPZ superdiffusion, and this was a joint work with the group of Norman Yao and Sarang Gopalakrishnan in the US. So let me first go back to the KPZ equation, and actually it's nice these days to talk about KPZ physics, of course, because the Nobel Prize to Parisi in October, although not for this work, but it's still among one of his most cited works in the field. And it's also a very important topic in mathematical physics, where Martin Heira was awarded the Fields Medal in 2014 for solving this stochastic partial differential equation. So what does this describe? So it describes the growth of height field. It comes from classical statistical physics. So you have a surface that you describe, which is given by a height at each point in space x, and point in time t. This is governed by this h of x of t. And you want to know, how does this height field grow and what kind of correlations emerge in this height field. Now, what you have, the standard term here would be something, a smoothing term, that describes if particles, are dropped from above onto the surface and they spread out, this would be some standard smoothing term. Then there's some fluctuation term describing this stochastic process of these particles randomly being dropped onto the surface. So this makes this a stochastic partial differential equation. So this h here is actually a fluctuating quantity. And then there's this nonlinear term, which was introduced by Kardar-Parisi-Zhang to describe a more realistic growth model. And this makes it nonlinear because you see now h enters and its gradient of h enters in quadratic term. So this makes it hard to solve mathematically. Actually, this is quite abound in physical systems, of classical physical systems. You see it, for example, in these surfaces of bacteria, tumor growth. There are beautiful experiments in the group of Katsumasa Takeuchi in Tokyo, who studied this in liquid crystals and really showed beautifully the statistics and correlations in these surfaces. Seems to also occur in traffic flow. I have here this nice video of a fluff fire. None of you have never seen this. The fluff, so the children apparently like this. If you go to YouTube, fluff fire is something children love. And the surface of this fire or forest fire fronts also obey this kind of KPZ universality class. Even if you put down your coffee and lift it up, coffee stains have that, surface of snow have that. So it's really a widespread thing in classical statistical physics. Now, there's a notion of now universality associated with it, which describes and characterizes all these systems in a uniform way, and we'll come to that in a second. So let me just give you an intuition of why this gradient term, this nonlinear term, is quite crucial for changing the growth of the surface. So imagine you have this kind of Tetris game where you drop blocks from above onto a surface. And now let's just imagine that each of the columns are completely independent from each other. This is what people call the random deposition model, or you could think of it as a non-sticky version of the Tetris. So the blocks just fall down from above independently into the different columns. And then there's a different version of the game, which is the KBZ version, when you have the gradient term. Whenever the block falls down and it touches onto a neighboring block, it will actually stick to that block. It will not fall down completely through the column. And that actually changes the dynamics of the surface growth actually quite dramatically, as you can see here. So this is how this looks like under this KPZ growth. And it looks very, very different from this random deposition model where you just have Gaussian fluctuations in the system. So already visually, you can see that introducing this term makes a huge difference onto how the surface grows and what kind of correlations emerge. Now, in general, we will be able then to say that this height field at x, t, let's consider a one-dimensional system, will grow with an average velocity. This will, of course, depend on the rate at which we're dropping particles from above onto the system. And then there will be fluctuations in the height field in each column. And the fluctuations, actually, interestingly, in this KPZ universality class, scale like t to the 1/3 compared to t to the 1/4 in the Gaussian fluctuation case. And this fluctuating function, this random variable that makes this the stochastic field here, the stochastic variable, this chi here is drawn from a distribution function, is a random variable drawn from a distribution function. And it's not a Gaussian distribution function here. In this case, it's this so-called Tracy-Widom distribution function, which is actually characterized by a distinct skewness in the system. So it's, for example, not symmetric, has a finite skewness. So this is something that characterizes this KPZ universality, quite different from Gaussian fluctuations. In addition, we have transverse correlations emerging of the height field. So the height field, because of the nonlinear gradient term, is correlated also over certain distances, which link distance and time with each other via the dynamical exponent z, where now this correlation length psi in the transverse direction is linked to the dynamical exponent z by t to the 1/z, with z being 3/2. So space and time are linked in this unique fashion of 3/2 compared to 1 for ballistic growth and 2 for diffusive growth. All right, so, well, everything I told you so far, you might wonder, is all about classical physics, and we're in a quantum workshop. So, but what was actually quite a surprise then in 2017 and 2019 was that a group of Tomasz Projan found that actually this KPZ universality seems to emerge also in closed quantum systems, in isolated quantum systems. Yeah? And what they found actually that it emerges at high, in parentheses, infinite temperatures. So we're talking about transport phenomena far away from the ground state transport phenomena of the system. So in the ground state, for example, of the 1D Heisenberg chain, you would have like this Tomonaga-Luttinger liquid behavior. But what we are talking about is this basically infinite temperature behavior of the system. And there was actually a nice paper by Joel Moore this year who showed actually that there's just a continuous crossover from the physics of this Tomonaga-Luttinger liquid to this KPZ universality class as you raise the temperature in the system. Now, what experiment can you do? So imagine you are in this infinite T environment of a Heisenberg quantum magnet and you want to probe the linear response of the system. So let's imagine then you place a spin up particle into the center of the chain. And then you ask basically, how does this spin spread as a function of time in this infinite temperature environment? And this is, of course, characterized by the dynamical spin-spin correlation functions. So we put the spin in here at position 0 at time 0, and we measure where is the spin a little bit later at time x, at time t, and position x. And I guess what your normal guess would have been if you wouldn't have known anything about the system, you would have said, well, probably Gaussian, yeah? Very likely to be Gaussian. So it's a Gaussian, and space and time are just linked to each other by this dynamical exponent of 2. Of course, you know, that's, as I just said, not true. That was the surprise that actually in this case, this does not hold true. And indeed, if you look at the dynamical spin correlation function of quantum, or actually also classical Heisenberg systems, then you find that this dynamical spin correlation function is given by a different function, this KPZ scaling function. It's not a Gaussian, and space and time are linked to each other via this dynamical exponent of 3/2 describing superdiffusive behavior in the system. Okay. All right, here are the data from Tomáš's group who showed that basically looking at this dynamical spin-spin correlation function, you see it's not a Gaussian, but it fits very well with this KPZ universality class. Now, Tomáš and his group also showed a little bit later or around the same time that another way to measure this dynamical spin-spin correlation function is to look at the melting of domain walls. So if you can prepare a domain wall, a sharp domain wall in your system where a little bit of the system is more spin up on the left and to the right it's a bit more spin down, then by looking at the evolution of this domain wall in the limit of the visibility of this domain wall going to 0, this is important actually to be in linear response, then you can show that the derivative of this domain wall magnetization profile directly corresponds to the spin-spin correlation function. It's just another way of getting at this spreading of this spin by looking at this, and this is the method we will use because it's a little bit easier to do in the experiment. Now, there was a conjecture now, that we know now that we have two quantities basically that behave like a KPZ scaling function. From the KPZ, from the quantum numerics, from Tomáš's numeric result, he found that this quantity is basically the KPZ scaling function. But we also know from the solutions of the KPZ equation, if we look at these correlations of the height field, so here I'm just looking at the height field at xt minus its value at 0, 0, and subtracting this average growth term squared. If I look at the correlation function of the height field, then it turns out that the second derivative of the correlation function of the height field actually also gives this KPZ scaling function. Okay. So now comes the conjecture that was made that if this is the KPZ scaling function and this is the KPZ scaling function, well, then maybe it is such that the hydrodynamics of the system is basically governed by the KPZ equation, and the magnetization operator in quantum mechanics is just given by the derivative of the height field operator of the stochastic variable. Okay, just by identifying those things to be the same, you identify the quantum operator to be the derivative of the height field in the system. And if you integrate the magnetization profile over space, you actually find then the quantity that is the polarization transfer. These are just the number of spins that have been transported in this domain wall experiment from left to right. So it's just the integrated magnetization profile. This basically corresponds to the height field at position 0 and time t in our KPZ equation. Okay, so that's all conjecture so for now. So that's not a proof, it's all conjecture, but this conjecture actually leads to measurable predictions that we can test in the experiment. So if this is true, then, for example, these fluctuations that emerge in the KPZ context, KPZ universality, should also emerge in the quantum variables that we're studying in our quantum system. Namely, for example, that the average polarization of the system should scale like t to the 1 over z, would be like t to the 2/3. So we should be able to see in the average number of spins transported that this gives us this dynamical exponent for the superdiffusive transport. And the fluctuations of the magnetization transfer, the fluctuations of the polarization transfer, they should be given, indeed, they should correspond to the fluctuations of the height field. And remember, the fluctuations of the height field, those were given by this Tracy-Widom distribution, and we're scaling like t to the 1/3. So we should see characteristics of both of that also in the fluctuations of the polarization transfer in the system. Okay, so before I come to our experiments, I should say there were actually experiments before ours in solid state systems in 1D spin chains by Alan Tennant's group, who looked at dynamical structure functions at higher temperatures in very close to 1D spin chains, and found actually at high temperatures a dynamical transport coefficient of 1.35, very close to the 1.5 we would expect for KPZ transport, showing that there indeed is first evidence for the superdiffusive transport. Now, what we're going to test in the experiment is the Heisenberg model. So in our case, we're going to do this with bosons, where we naturally have a ferromagnetic Heisenberg coupling. We're going to do this at infinite temperature in the Heisenberg regime, so delta equals 1 here. And we're going to check how the system behaves when we break certain symmetries in the system. So far, the understanding is of the system that integrability and non-abelian SU2 symmetry or any non-abelian spin symmetry play a crucial role for observing this KPZ dynamics. Yeah? So we can test that in the experiment. We can, for example, break integrability by going to 2D by just increasing the transverse coupling, or we can break the SU2 symmetry by increasing magnetization in the system, looking how that system behaves. All right, so the system we then have is, as I said, our flattened system. We have 1D systems now available with 50 spins, which is nice. So that makes it much bigger than what we've been able to do before in the systems. And the 2D systems, as I said, are about like 1,000 systems, 1,000 to 2,000 particles that we can observe. So in these flat box potentials, okay, so that's nice. Okay, so here are some data on that. So here's such a system where we start, for example, preparing a domain wall, where to the left, we have all the atoms spin up, and to the right, we have all the atoms spin down. And then we can basically let the system evolve. And the density always stays unit density because we're in the strongly Mott insulating regime of the system. But when the spins move, you see in the time dynamics, these spin downs move into the region of the spin ups, and vice versa, the spin ups move into the region of the spin down. So just by counting here the number of spins that have been transferred, I can get each snapshot, the polarization transfer for a given snapshot, and I can calculate this distribution function of polarization transfer in my system and also the average polarization transfer. Now, we can do this also with clean domain walls, but also with reduced visibility domain walls. And this is important to be closer to this linear response regime, as I said. So we're basically trying to mimic an initial state in the domain wall with a finite visibility where we take this eta basically going to 0. That's the initial state we're basically preparing the system. So here's the first data where we look at the average polarization transfer as a function of time over about 50 tunneling times in the system, exchange times. So this is quite a long evolution time. This is pretty much also close to the limit of what DMRG is able to do in the 1D case. And you see actually already for this polarization transfer, when we fit this, it fits nicely to the superdiffusive transport with a transport coefficient 1.54 with an error of 7. And you can see the individual magnetization profiles at different times here. We can also just rescale them by this t to the 2/3 and get this collapse of these magnetization profiles in the system. Just to compare also to ballistic transport, the blue curve and the red curve, red line would be diffusive transport. You see that it's something completely different to either of those situations. Yeah. Then we can do this check that I said. We can go from 1D to 2D. So we can go from this interchain coupling 0 to full interchain coupling to the full 1,000 particle 2D system. And we do the experiment, and you see there actually the transport coefficient goes from this KPZ value 1.5 back to diffusive in the system. Okay. We can magnetize the system, so we can break this SU2 symmetry by putting an excess number of spin ups, for example, into the system. And you can see now, if you look at the magnetization profiles, here's the unmagnetized case and here's the magnetized case, and you can immediately see a ballistic wing of very fast quasi-particles in the system spreading much faster. And also the average polarization now does not behave superdiffusive anymore, but is more in the linear ballistic transport regime of the system. So we can indeed see this ballistic transport. So if we summarize the transport data, we see that we can have, for 1D system unmagnetized, we have superdiffusive KPZ type transport, or at least superdiffusive transport compatible with KPZ, I should phrase it like this. 1D magnetized, we get ballistic transport. 2D unmagnetized, we get diffusive transport back in again. So indeed, when we break those symmetries, we always go away from this superdiffusive transport regime. Now, one thing that is much more important than superdiffusion alone does not show enough proof of KPZ physics yet, one thing that you can additionally test is, I said, the fluctuations. To look at the fluctuations of the height field, which would scale like t to the 1/3, and there was this Tracy-Widom distribution, which would be very different from the Gaussian, characterizing the fluctuations. And remember, the height field fluctuations would manifest themselves in our case as polarization fluctuations in our system. So that's what we can look at. Compare 1D to 2D. So here's the standard deviation of our polarization transfer data for 1D and 2D. 1D is green and 2D is the red data. And for 1D, you indeed find this 0.31 in very good agreement with the 1/3 that you expect for KPZ dynamics. And if we look at the skewness of the data, we always see that for the 1D data, we always seem to remain with the finite skewness of the system, which is compatible with what we expect and close actually to the value that we indeed also numerically expect for these Tracy-Widom distributions, whereas in the 2D case, it seems to be more compatible, at least with the decay in the system, which you would expect for a Gaussian fluctuating system. All right, actually, there's we can ask already a little bit, why is there superdiffusion? I think right now we have, and from GHD dynamics, so it would have been good to have Benjamin's talk before mine, but so from GHD, actually, there's pretty good understanding of the superdiffusive part. However, there's, I think, no theory still right now which explains the full context of the fluctuations and everything. So we kind of can understand the superdiffusion, the transport behavior, but we don't have yet a theory which can explain the full kind of KPZ behavior that we expect in this system, or that numerics and experiment now both show in the experiment. So one way to basically understand why you get superdiffusion here is to basically start from the unmagnetized, from the magnetized case. And remember that in the magnetized trace, we had ballistic transport with velocity scaling proportional to delta, to the magnetization in the system. Now, of course, we are at this unmagnetized point where we have superdiffusion, but of course, we're in a fluctuating system. So random fluctuations of the spins will lead to typical magnetizations in a region of size L, given by 1/√L, okay? And now if we can just ask, what is the spin transport time across L? Well, in this kind of magnetized region, that would just be proportional to L divided by this typical magnetization 1/√L gives us this L to the 3/2 behavior, showing indeed the superdiffusive transport. So just from these basic arguments, very simple arguments, you can understand this superdiffusive scaling in the system. Yeah, but as I said, I don't think there's yet a full understanding why KPZ universality emerges on an analytical level. And it would be nice, of course, to see that in these higher order quantities, in these fluctuation quantities as well, compared to the transport data. Okay, let me summarize. So I showed you that we have observed superdiffusive transport at the Heisenberg point in our 50 spin Heisenberg quantum simulator, but we have to be careful because superdiffusion alone can also arise from linear models. We've, however, also observed polarization fluctuations with this 1/3 scale, and we've observed the skewness of this polarization fluctuations, which is compatible with what we expect from the Tracy-Widom distribution. And also by breaking fundamental symmetries in the system, we seem to be able to destroy this KPZ behavior. Just one final comment. There have been other experiments. Actually, Michael was involved in them. We discussed them early when we did these in 2014 already. We studied spin transport in 1D and 2D systems via spin spirals. And by imprinting basically spin wave vectors onto a Heisenberg quantum magnet and then looking at the decay of those spin spirals. And of course, you do that for all wave vectors, then you can extract basically also the dynamical transport coefficient in the system. Now, we did this in 2014, and we found for the 1D system actually diffusive behavior, 1.9. Wolfgang Ketteler did this in 2020, again, a very similar experiment with tunable XXZ couplings, and found at the Heisenberg point also 1.8. So we redid the experiment just to be sure about this old measurement. We redid the experiment, the spin spiral experiment, and found 2.0, so very clearly pointing towards diffusion. And I think the answer to this is that basically these spin spiral experiments do not probe equilibrium transport, They seem to be falling in a special class here, giving us non-equilibrium dynamics. And I think a clear understanding is missing. They also probe much shorter evolution times, but this is something to be resolved. All right, so let me thank the team working on this. The main person who did the experiment was actually David Way, and the experiment is now led by Johannes, and Tony also had a big contribution to this experiment. All right, thanks a lot for your attention.